So there's sorry. This starts with other types of games. That's quite strange to start with something that's other than something else, but we don't know what that something else was. Unless we remember what kind of games we were looking at last week. So what kind of games were we looking at last week? Where's Jake? I really need Jake because he answers all the questions and asks more questions. So somebody else has to take over that one. Volunteers? Ready? What kind of games were we looking at last week?
Two-player competitive.
Two-player competitive games. Yes. Well, competitive as opposed to non-coalition or non-cooperative? Okay, yes. So we were looking at games where there is no cooperation between the players. We were looking at players where there are only, games where there are only two players, so not multiplayer games. We'll have a look at multiplayer games briefly at the end of the term. And we were looking at games that we called strategic games, that were not sequential moves. So a strategic game we said was, you have a number of players, we have two, they both decide on what strategy or what action they're going to take, and then simultaneously, without knowing the other player's decision, they act. Okay, so that is what is called a strategic game, and that was the kind of thing that we were looking at. And so even if you see that, if you think that some games don't really look like this, so for example, we'll come to the game of rock, paper, scissors. Who doesn't know rock, paper, scissors? Everybody knows? That's good. Reassuring. So there, even if you're playing several times in a row, each of these occasions is really a separate one, because what you do doesn't really depend, in theory, on what happened before. So of course, you can start thinking about some psychological tricks, how to gain an advantage or something like that. But in theory, in the simple model that we're looking at, it doesn't matter what happened before, and you should always play the same. Okay. So this is just to remind us what games we are not currently looking at. And what we're looking at is two players, a strategic game where they take their action at the same time. And more specifically, we were looking at zero-sum games. And zero-sum games are sort of the games where, when you look at the outcome, where one player is winning, the other player is losing. So there can't be an outcome of the game where they're both very happy. Okay, these kind of games do exist, and we'll look at them afterwards. But first, let's do the zero-sum games. All right. Yeah. What this is about is that we're doing our analysis under these two assumptions. The first assumption that is there is rational choice. Okay, so that's the thing that we were talking about before, wasn't it? We were talking about preferences, and we said that we express these preferences of a player by a payoff function, and that function is if the player prefers a certain result to another, then the function will be better, larger on that certain result than on that other one. Okay? And of course there is a lot of discussion about, and there were some questions. For example, how about if when we were looking at the pub managers game, that sounds familiar. For example, what if a certain pub managers goal is not to maximize the amount of money that they take in, but instead to minimize the amount of money that the other player takes in, or something like that, you know? So of course, people could have various objectives. Some people are altruistic, so what they perceive as good for themselves is when somebody else benefits, and so on. But what we're assuming is that when we get the payoff function, that expresses those preferences of that particular player. Okay, so if it's a player whose aim is to make everybody else benefit, then the payoff function is going to be large for in those situations where other people benefit. Okay? And so all the preferences of that particular player are just summed up by this payoff function, and there's no discussion about for us at the moment. There's no discussion about how we arrived at this payoff function. Does that make sense? Okay, so all the information about the preferences of that player, no matter how they decide, are summed up in that payoff function. And moreover, we're assuming that the way they act when actually playing the game is that there's this rational choice assumption, which is that they actually choose the actions for themselves that are going to lead to the maximum payoff that they can get. Okay, so they're actually maximizing doing the actions that leads to what they prefer, rather than just doing something random and not thinking about it. That's the first assumption, and the second assumption is that everybody knows everything about the game. Okay, so we think that, or we're assuming that all the players know everything about the game, including all the possible actions of all the players that are there, and also including all the preferences of all the players that are there. And under this assumption, we're going to try and analyze the game. Okay. Any questions about this? Where's Jake? I really need to ask a question. But since he's not here, I have to ask a question for Jake. And I'm not going to invent one. I'm going to ask the question that he asked last. So what is the goal when we're trying to analyze or solve a game like this? Is it to find the dominant strategy or something like that? And the answer is no, not really, because the aim is to determine what's going to happen. So which of the actions the players are going to play. So when we're given a game, like we were looking at the Pub Managers game, do you remember it? Shall I show it? Well, anyway, we were looking at the Pub Managers game where the question was whether each of the managers should introduce a special offer or not. And we determined that most likely, under these assumptions, acting rationally, both pubs are going to introduce a special offer. Okay, but we solved it, and that's the kind of answer that we're looking for. But it's not always going to be so easy. So that's an important definition. Read it. Okay, so So when we're trying to determine what the players are going to do, what they are perhaps going to do, or we believe what they're going to do is, if there is a game which has what's called a Nash equilibrium, then they're going to play the actions that lead to a Nash equilibrium. Okay? Because when they're doing this, then none of the players, there can be two or more, none of the players, so think of two or multiplayer game, none of them has any incentive to do something else than what they're doing. Because if they started doing something else than what they're doing, they would be losing out. And so this is kind of an assumption that, not an assumption, but seems unavoidable that if there is a Nash equilibrium, and it can be found quickly by the players, then what they're going to do is they're going to stick to it and not experiment and not change to anything else. Okay, so that's the idea of the whole analysis of a game, is to find these equilibria. And if we can find them, then, well, the game can have one or more Nash equilibria. And if we can find them, then we somehow think that that's what the players are going to do under our assumptions. So if you look at a payoff matrix, which looks like this: 2, 2, 3, 1, 1, 2, and 4, 4. So this is the row player's has two possible actions, and I'm not saying what they are. And the column player has two possible actions, and we don't know what they are, but we don't know. Because we're just looking at the mathematical model, not what situation we present. So look at so what are they? These are the payoffs of the two players. The first number is the payoff of the row player. The second number is always the payoff of the column player. Okay. And so the row player has two actions, the first one and the second one. The column player has the first one and the second one. And for example, if both of them decide to play their first action, then they're both earning 2. So you can see here that if they both have chosen the first action, then is the row player going to have an incentive to switch to the other action? No, because their payoff will go from 2 to 1. So they prefer staying with the first action as long as the column player doesn't switch. And the column player, is the column player going to switch to the other action? Well, no, because they will go from 2 to 1. So they prefer staying in this situation where both players are playing first strategy rather than switching to the other. Okay. Does that make any sense? Everyone's asleep. Wake up. So the combination of so there are two actions. We call them 1 and 2 for the row player, and then there are actions A and B for the column player. So the action profile one for the row player and A for the column player is a Nash equilibrium. Because, well, if row switches to playing 2, the payoff decreases. So from 2, it'll be 1. And if C switches to playing B, then the payoff also decreases. And by accident, it's also from 2 to 1. Is there any other equilibrium in this game?
2 and B.
2 and B. Why is that? Because what is higher? Okay, yes, you're right. It's 2 and B. So this is another Nash equilibrium. Okay, so that's an important kind of point. So this is better for everyone, is it not? So that's kind of a good Nash equilibrium, but this is also an equilibrium. So it might happen that for some reasons, but depending on what the game is, they could still be playing this, even though, because nobody, well, you know, so think of okay. So the definition of the Nash equilibrium or of an equilibrium is like this. So it is that when you're in a point where you know what everybody is playing, then in that particular point, you have to look at every one of the players individually. Okay? And you're assuming that, so I'm looking at the rogue player. I'm looking at, given that the other player sticks with A, am I better off switching to something else? No. And then I'm looking from the point of view of the second player. If the rogue player sticks to 1, am I better off switching? Well, no. This is really the core of the notion of a Nash equilibrium. It's not that it's the best possible outcome for everyone, which really exists. But it's one where if the other players stick to what they're doing, you can't improve. Nobody can. So for example, and then you don't really know what's going to happen. So, for example, this is a bit of a joke, really, but I'll do it anyway. So, there are two drivers of a car going against each other on a road, okay, and now they can either
go towards the left side of the road or towards the right side of the road. So the first driver can go left or right, and the second driver can go left or right. Okay, and so if the first driver goes left and the second driver goes right, they don't like it because they crash. And if the first driver goes right and the second driver goes left, then they also crash. So they don't like that very much. And if they both go right, then they pass. So they prefer this. Okay. But of course, we all know that it's much better to go left because we know that. So that's even more preferable. So you have this game where you have two drivers, and what are they going to do when they meet? Is, well, there are two equilibria just like that. So there's this equilibrium where they both go right, and there's this one where they both go left. And even though this one is better than that one, in many countries they will do this. Okay, this is a bit of a joke, but you see the outcome. What it's trying to say is that a Nash equilibrium does not necessarily have to be the best point in the game for everyone. Let's move on. So that's the notion of a Nash equilibrium, and our aim for, well, today and next week is to learn how to find Nash equilibria in zero-sum games. Okay, so these things. So what is a zero-sum game? A zero-sum game is a game where the payoffs, when you look at the payoff matrix, then the sum in each of the entries in the matrix of the two numbers is the same number. So what we're assuming is that the same number is 0. And so what we're writing for a zero-sum game is just the payoffs of the row player. And we'll call the row player blue. And we'll call the column player red from now on. So what we write is 5, that's the payoff for the blue player if blue plays B3 and red plays R1, whatever those strategies are. And for that same action profile, for the center combination B3, R1, the other player's payoff is -5. Okay? We're just assuming that it's the opposite number. So payoff matrix, the payoff matrix only contains the payoffs for the row player and the other player's preferences, because it's a zero-sum game, are the opposite. So it doesn't fit. Okay, as I said, the goal that we have is find a Nash equilibrium. I'll only say equilibrium. What I mean is a Nash equilibrium. It's, I'll use it interchangeably. And the first step should always be to look for dominated strategies. So as a reminder, a dominated strategy is one that is always worse than some other strategy, no matter what the other player is doing. Okay? Can anybody see a dominated strategy? You don't get the dominated strategy? Oh, you don't get the matrix. Why don't you ask? Is there anybody else who doesn't get the matrix? See, nobody else asks. They're all watching Charlotte or can't be bothered. Probably just can't be bothered. They think it's all going to happen by itself. Okay. So what is the matrix? Does anybody know what the matrix is at all? Anybody else? Oh, it's the matrix of a game. That gives us the payoff. Okay, so we're looking at matrices with payoffs. Well, so there is a game. The game has two players. I call them blue and I call them red. Each of the players has 4 different available actions or strategies. I call them B1, B2, B3, and B4. And it doesn't matter to me what they are in real life, because this is a mathematical model. So just like when you're doing the simplex method, you can get given x1, x2, x3, and you don't know what they mean. Okay? You're trying to solve the problem, the mathematical problem. And you solve it, and you say x1 is 7, and x2 is 3. And that's a solution to the mathematical problem. But this is a similar sort of mathematical problem. It comes from some real-life situation, but we don't care about the real-life situation now, because now we're doing the maths of it. And once we've learned how to do the maths of it, we're going to go back, just like we did in linear programming, and see how real-life situations give rise to things like that. Okay? But now what we're doing is we're looking at mathematical. The model is the blue player can do one of 4 things: B1, B2, B3, and B4. And the red player decides to do R1, R2, R3, or R4. And then, at once, they do it. And what do these numbers mean? These numbers express the preferences of the blue player. So for example, if blue does B1 and red does R1, there's a number 2. And if blue does B4 and red does R2, there's a number 0. That means that the blue player is happier if the outcome is going to be yes, it would be B1 and R1, than if the outcome is going to be B4 and R2. But they would be even happier if the outcome was I'm playing B1 and the other guy is playing R2. They would be the most happy if we were playing B3 and red was playing R1. Okay? And because it's a zero-sum game, the happier the blue player is, the unhappier the red player is. That's a property of zero-sum game. Okay? So one player is in a zero-sum game, The happier one player is, the unhappier the other player is. Okay? You now get the matrix. Good.
So at least one person now gets the matrix. So a dominated strategy is one which a player is never going to do, because no matter what the other player does, there's always something. There's always something. Yes, there's another. Okay, no, wrong. Wrong. I said it wrong.
Oh, but so I'll say it right. Dominated. A dominated strategy is one where there is a dominated strategy is not good because there is another strategy or action, that's the same thing, which is always better no matter what the other player does. For example, B4 is a dominated strategy because B3 is always better. Okay? So if red decides to play R1, blue is better off with B3 than B4. And if it's R2, then the blue player is better off with B3 than B4. And if red decides to play R3, then the blue player is better off with B3 than B4. And if red decides to play R4, then again, blue is better off with B3 than B4. So B4 doesn't make any sense for the blue player, right? It's called dominated by another strategy. So it goes away. And you see any other dominated strategies now that you probably know what's going on? Hopefully. Can you? B2, is it dominated by which one? So B2 dominated by B3 as well. Yes, because 5 is better than 0, 2 is better than -1, 1 is better than 0, and yes. So B2 dominated by B3, and B4 dominated by B3 also. B4 dominated. Anything else? So now, look at R2 and R3. 4 is larger than -1. -1 is, this never happens. 2 is larger than 1, and this never happens. Four larger than -1, 2 is larger than 1, and these two never happen. So, what does that say about R2 and R3? Anyone of them better for the red player than the other? Which one is better? No. I wanted the wrong answer. because you learn from wrong answers. You don't learn much from correct answers. R3 is better for the red player because remember, this is the payoff. This is the happiness of the blue player. The happiness of the red player is the opposite thing. So the red player is much happier here than in the 4, and the red player is much happier in the 1 than in the 2. Well, a little bit happier. Okay? So the red player won't ever do R2 because R2 is R2 now dominated by R3. And if you compare R3 and R1, what do you see? R1 is also dominated because R3 is always a lower number. So R1 and R2 are now dominated. So we've only got these 4 possible outcomes now left because we know that blue is never going to do B2 or B4, and we know that red is never going to do R1 or R2. Right? But now, blue is never going to do B1 either because B3 is always better. So, so now this goes away. And now also this goes away because the red player now knows from perfect information that the blue player is going to play B3, and so there's no point playing R4 because that is better. So like this, we've concluded that there is only one equilibrium. And so we see that the blue player will necessarily play B3. And so B3, R3 is an equilibrium. So checking that it really is an equilibrium, you can see that the blue player, as long as red is sticking to R3, the blue player can't improve. From 1, they would go to 0, minus 1 or 0. And they don't want to do that. And at the same time, the red player cannot improve because from 1, they don't want to go to 5, 2, or 3 because that's the happiness of the blue player, not the red player. So it's their unhappiness, as it were. So they want to have a number that is as small as possible. Okay. That's another proof that it's an equilibrium. We found it by looking for dominated strategies, but we can also see that it is an equilibrium, in fact. Okay, any questions? Now let's have a look at this. Okay, so that's another game.
Are there any dominated strategies? Well, B1 is better than B2 here, but worse here. B2 is better than B3 here, but worse there. B1 and B3, B1 is better than B3 here, but worse there. So blue doesn't have any dominated strategy. And similarly, you can check for red. So R2, this is better, this is worse. So R2 and R1 is an elimination. R2 and R3, this is better, but this is worse. And R1 and R3, this is better, but this is worse. So for the red player, there are no dominated strategies.
So there are no dominated strategies. Yeah. Which means that we have to do something else. And what else we do is what we'll learn next week. Because we are out of time, I think. So, any questions or comments or objections? If you haven't got the book, grab the book on your way out. And we'll see you.